Chapter 6 is going to be covering solving differential equations through the use of series. And it's going to be necessary for us to review a few things about series in this video, and we're also actually going to solve one differential equation with series at the end as well. A power series in the form of x minus a, which we're going to call a Taylor series, is an infinite series when we are summing from n equals 0 to infinity of some arbitrary constant c sub n times x minus a raised up to the n. The series is said to be centered at a. When x is equal to a itself, that series would have trivial convergence. You can see every parentheses would collapse down to 0. The series is also very convenient when a equals 0, when n equals 0, where a equals 0, that would be called a Maclaurin series. So a lot of this we are reviewing from BC Calculus. Convergence. If x is a specific value, remember x represents numbers, perhaps x could equal a half or negative 1/3, the terms of this infinite power series become constants then. And if the series equals a finite real number, the series converges. And if not, it's said to diverge. The interval of convergence. Every power series has an interval of convergence consisting of all numbers x for which the series converges. The center of convergence is the value a at which the power series is centered. Now, the radius of convergence, you might remember from the ratio test. So very often we would do a test to determine where a series would converge. It would lead us up very often to a statement like this, that the absolute value of x minus a was less than r. We'd get three different possibilities that could occur for a radius of convergence. We could have convergence only at a center a, in which case r is equal to 0. What this means is, for number 1, you never get complete divergence for a power series. You would at the very least have convergence at a. But very often you can see that from the ratio test we could arrive at the absolute value of x minus a is less than r. This would be our radius of convergence, and of course we could then test endpoints. We'll talk about that in just a moment. Of course then our series would diverge for x minus a greater than r. It's also quite possible that our series would converge for all real values. Now what I wanted to show you is from that ratio test, if you solve to get the absolute value of x minus a less than r, just some algebra 2 work here, this would be equivalent to saying the opposite of r is less than x minus a less than r. If we add an a to all three parts of this inequality, we would arrive at this inequality, that a minus r is less than x is less than a plus r. This will correspond to a number of different possible intervals of convergence. Of course, the big question is, do the endpoints also converge? Well, this top statement here would be that instance where the left and the right endpoints do in fact converge. You could have one of your two endpoints converging. We could see that happening in the next two examples. Or perhaps neither of the endpoints converge. So that's how an interval could appear if it's not pointwise convergence or all reals. Absolute convergence. Within an interval of convergence, a power series converges absolutely. That means it converges in absolute value. And then finding this interval of convergence, we already talked about using the ratio test. Taking the limit of the n plus 1 term divided by the nth term. If you arrive at L, some real value limit, and if that L is less than 1, then we have convergence. In fact, we have absolute convergence, which leads to regular convergence. So the radius could be found quickly through the solving of this inequality. The radius is actually on the right side. I should say the interval is found by solving that inequality. Okay, so if r is greater than 0, then f is continuous, differentiable, and integrable on that interval. We could take derivatives or integrate. Being analytic at a point. Real quick review here. A function is analytic at a point if it can be represented by a power series in x minus a with a positive radius of convergence. You might remember last year in BC, we memorized several very, very important power series. And we're going to bring these back. We really are going to refer to them from time to time here. You might remember what e to the x would look like. Here's its Maclaurin series. We can say dot, dot, dot. This would be sigma from n equals 0 to infinity of x to the n divided by n factorial. Might wonder, what about sine of x? Well, sine of x was x minus x cubed all over 3 factorial. By the way, down here you can even say 1 factorial for your x, plus x to the 5th over 5 factorial, minus x to the 7th over 7 factorial, and so on. Well, what would this look like in terms of sigma? Well, you can see it's alternating. You're going between positive and negative values of your terms. Let's have negative 1 to the n. Start at n equals 0. Odd powers. What would odd powers look like? Well, perhaps 2n plus 1 would suffice. Down below we have factorials that are going to have the same exponent value in front of the factorial. So we'd have 2n plus 1 factorial. And then for cosine of x, one final very important Maclaurin series that we need to remember. We have 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. And a nice way to remember this is that cosine is even. So this will become negative 1 to the n. And a way to nicely write this exponent would just be 2n. We're going to divide by 2n factorial. And all of these converge for all reals. It would be an infinite radius of convergence. That's the wonderful part of those very special 3. But of course, this is a differential equations class. And you might wonder why we're bringing back series. Sometimes solving a differential equation is just going to be excessively difficult by the other methods that we've studied thus far this year. You'll find that you just don't meet those special conditions. You might wonder, is there another way we can proceed? We can. We can assume a solution is of the form y equals a power series n equals 0 to infinity of c sub n x to the n. The wonderful thing about this is that this power series could represent e to the x, sine of x, cosine of x, perhaps even something involving the natural log of x, many, many, many other functions. So you can see the advantage in using this method. Well, let's take a derivative. Now, something to remember about taking derivatives, hopefully you remember this in BC, we're going to lose our first term. And we're going to drop down an n, and this is x to the n minus 1. Use that power rule. Sometimes kids are looking at that thinking, wait a minute, why are we not writing n equals 0 anymore? Let's expand the original y. Why is this power series? The 0th term we'd have c sub 0 x to the 0. At the n equals 1 we'd have c sub 1 x to the 1, c sub 2 x squared, and so on. your derivative is going to wipe out a constant. And what you're going to see immediately is that you're just left then with taking the derivative of c1x, which is just going to be a c sub 1. So that's why we always lose one of our counters. We're going to have a constant, take a derivative of it, and it vanishes. With that in mind, we can also say y double prime. Well, once again, we're going to lose another constant. Imagine that I'm now taking a second derivative here. If I would have taken my first derivative, the derivative of c1x would just be c1. Take another derivative, that's gone. So that's why we lose that. We've got c sub n, here's n. But then don't forget, we're going to bring down n minus 1. And then we'll have x to the n minus 2. Now we're going to substitute these into our differential equation. And when we do that, well, actually, tell you what, we didn't even need to take a second derivative here. Forgive me for doing that. But look, we're going to just plug in this first derivative. That's going to be c sub n times n x to the n minus 1 with our sigma going from n equals 1 all the way up to infinity. We say minus 2x. And what's y? Well, y is just from n equals 0 to infinity of c sub n x to the n. And we have this equal to 0. So we've got some work here with our sigma. Tell you what, I'm going to do a little bit of cleaning up here. We're going to just have n equals 1 to infinity. Here's c sub n times n x to the n minus 1. I'm going to actually multiply the 2 and the x inside here. And when I multiply x to the n, this will become x to the n plus 1. Now at this point, you might notice that our sigmas are looking very different. They're looking very different primarily because our powers of x are not the same. And that's actually a huge concern. It's preventing us from being able to combine these two series into one. And ultimately, that is our goal. We might have multiple sigmas in a problem, but we would like to condense them into one. And what we're about to do, we're going to do extensively in this chapter. This is called re-indexing. Take a look at your first sigma. I'm going to say, let's let k equal n minus 1. My counter right now is n. I'm going to have a new counter. We'll call it k. And I'm deliberately looking at the power of x and saying, I want to call that a k. Now, in a very similar way, I'm going to come over here. I'm going to use a different color also. And I'm going to say, do you know what? This new power of x in this other sigma, I'd also like to call a k. This time k is equal to n plus 1. Now, what we're going to do right now is completely rewrite both sigmas with these new k values substituted in. Now look, my counter was n equals 1, but if I plug in n equals 1 to k equals n minus 1, I'd see that k equaled 0. We're still going to go up to infinity. N itself here would equal k plus 1. So I'll have c, but my new subscript down here will no longer be n. N is k plus 1. And here's another n. I'm going to rewrite that as k plus 1. Then I'll have this as x, raise it up to the k. Well, tell you what, we're going to do the same thing with our second sigma. Look, if n is equal to 0, here we'll get k is equal to 1. N would be k minus 1. And then we'll just have x to the k. So if you're looking right now, you're going to see that with this new substitution, at the very least, we have an x to the k and an x to the k. The problem is we'd like to also begin at the same counter, and we're going to deal with that in just a moment in our next video.